And finally, let's talk about second order reactions. So once again, if we look at the graphs of the concentration of A versus time, and so this is a second order reaction, and we're looking at, just the concentration of A turning into B, and we're saying that this is second order, which means that the rate is equal to, it would be, there could be several things. We'll just say it's K times the concentration of A squared. So any overall second order reaction. If we look at just the concentration versus time, we see that it's curved. That's going to be hard to calculate any point in time. If we do the natural log of the concentration like we did for the first order reaction, we still get a curve. In order to get that straight line graph, what we need to do now is the reciprocal of the concentration of A versus time. And when we do that, we do get a straight line that we can use in other equations. So here's that equation again, or the integration again. We start off with our just rate laws, where we say that the rate is equal to the change in A versus time, and that would be the same as the reaction constant or the rate constant times the concentration squared. So an overall rate of second. And this can be integrated using calculus and give us this guy right here. So this is just put into a form where we get that straight line graph that we can use later on down the road. A naught and A times still mean the same thing, initial and concentrations after some period of time. When we do this, we get that straight line, which means we wind up with a slope, we wind up with our y-intercept, and we have our y value. So what this means is, once more, this reaction, our integrated rate law, can be rearranged. So it started out as 1 divided by the concentration of A at a time minus the reciprocal of A initially equal to the rate constant times time. And if we rearrange that once more just to solve for the concentration of A after a given period of time, because that's what we're most interested in, we would see that it's K times T plus 1 over A naught. And so what does that mean for us? Well, it shows us that y equals m times x plus b, where our y value is the reciprocal, our slope is still the rate constant, time is still x, and b is the reciprocal of our initial concentration. So we can use the slope to find our k, and it's not a negative this time, we can see it's a positive slope, and we wind up with all the pieces we need to solve anywhere along the line. You need to be able to recognize a second order reaction from this graph. So if you see a graph of the reciprocal of the concentration of A versus time, and you get a straight line, that means it is second order. If it's the natural log of A versus time, and you get a straight line, that is a first order. Let's take a look at a great question here. So we're looking at nitrogen dioxide again, and it's decomposing into nitrous oxide and oxygen gas. Using this data provided, so we've got a data table here, and we've got two graphs of this information right here. So this one shows the reciprocal of the concentration of nitrogen dioxide. This one shows the natural log of the concentration of nitrogen dioxide. We need to find the rate law, and we need to find the rate constant. So that first question, find the rate law. So we know that rate is equal to the K value times the concentration of NO2. The question is, what power is it raised to? Is this a first order reaction or is this a second order reaction? We have two graphs over here that will help us answer that question. So this one right here shows a curved line when we have natural log versus concentration. This one shows us the straight line, and it's 1 over the concentration. So the one that shows us the straight line is the one that tells us the order, and the 1 over concentration means it's a second order reaction. If it was a straight line here, it would be a first order, but since it's this guy that we're looking at, that tells us this is a first order reaction, or second order reaction, so it would be concentration squared. Now we just need to find the rate constant, which is K. So we can take the integrated rate law, we can rearrange it to solve for K. And it would be 1 over the concentration of A at a time minus 1 over the concentration of A initially divided by the time. And I'll just use those first two data points again on our chart. So we're starting with time 0 and ending at 100 seconds. And so it would be 1 over the final concentration, which is 0.015 molar, minus 1 over the concentration initially, which was 0.070 molar, divided by the change in time, and the change in time was 1.0 times 10 to the second seconds. And so if we solve this out, we find out that the rate constant for this one is 0.52. Now, what are the units? Let's practice on canceling out units to figure out what the units are for a second order reaction rate constant. We have molarity minus molarity. That's not going to cancel out because they're both on the bottom, so they're both on the same side. No natural logs here to wave their hands and make them disappear. Those will both stay. We also have seconds on the bottom. So what we're winding up with here then is molarity inverse, because it's on the bottom, as well as seconds inverse. And it's not molarity squared because those molarities are not multiplied by each other, they're subtracted. So the units of this particular second order reaction are molarity inverse times seconds inverse. Another way of saying that same thing is 0.52, 1 over molarity seconds. Okay. Hey, keep in mind for a second order reaction, they can be written different ways, and so we don't always end up with the same units on our rate constant for a second order reaction. They change depending on the way it's written. Last thing I want to show you is just how a zero order reaction would look on a graph. So zero order reactions, they're not very common, but you will see them occasionally. What this means is that the reactants themselves have no effect on how the reaction proceeds. It's some intermediates that we'll talk about a little bit later down the road. So if we take a look at these three graphs, we end up getting a straight line when we just plot concentration versus time for a zero order reaction. That means as the concentration decreases, the rate stays the same. So it's not going to change, it's just going to steadily decrease over time. So really the rate is constant in a zero order reaction. So concentration of A does not make any difference for the rate. And if we were to do the natural log or the inverse, we would see that we get curve. So you recognize a zero order reaction because we wind up with a straight line when we plot just the concentration versus time.